Okay, so let's briefly recap the things that we were discussing last time. So after we discussed the NERF, we also discussed some of the ideas in terms of like how we can leverage some kind of some other representations in a way that we can also speed up all the computation of the NERF. So we saw that NERF is actually quite slow, both in the optimization time and also in the rendering time, because like everything is basically encoded in a single the global DNLP, network. So the idea that we discussed last time is basically how we can also speed up all the computation by using some kind of the hybrid representation. So the idea of the plan of cells was basically making some kind of the neural net free the NERF the pipeline in a way that we are encoding everything in some kind of the 3D voxels. So it was basically a simple idea in terms of that we're having the 3D grid. And for each of the corner points of the 3D grid, we are basically encoding the opacity values. And also, for each of the samples along the array, we are basically interpolating all the opacity values coming from all the corner points of this 3D grid. Then the question is that basically how we can also encode the radiance information, because as we have seen last time, basically the radiance is kind of the information which is not just kind of the value for each of the point, but it's actually kind of the function which is defined with the view direction, right? Actually, we could see that the radiance is kind of the function which is defined over the unit sphere. Then the question was that what would be kind of the best way to approximate this kind of the radiance the function defined over the unit sphere with some kind of the discretized some of the samples. And the basic idea that we discussed last time was basically leveraging the speaker harmonics, which is kind of the basis function. We can do some kind of the phrases, kind of some transformation, basically representing all the kind of the function as kind of the linear combination of this kind of the basis function. So by using the speaker harmonics, now we could basically represent all the radiance function with some kind of the coefficients of the low order the basis function, the speaker harmonics, and now we are encoding all these kind of the coefficients for each of the grid in the corner points, sorry, in this 3D grid in a way that now we can interpolate not only the opacity values, but we are also evaluating the radiance function for each of the corner points and also interpolating the radiance as well, and then getting the information for each of the samples along the array. So that is kind of the idea that we can also run basically the NERF without having any neural network, but by basically encoding all the information in the 3D grid. So these are basically two extreme cases. Like one is basically the vanilla NERF case that we are encoding everything in the single neural network. And the other case was basically encoding everything as kind of some per voxel information. So we are encoding the opacity and also the speaker harmonic the coefficients for each of the radius function for each of the corner points. So there are basically the pros and the cons. The good thing of the NERF is that it's basically very compact representation because everything is encoded it has kind of the parameters in the neural network. But the problem is that it's quite slow. And the plan also was basically the opposite case that is quite fast, but it's also very memory heavy because everything is basically discretized in this 3D space. So kind of the hybrid, the version was basically now we are encoding, storing not directly the opacity and the radius information, but basically storing some kind of the feature vectors that can be basically decoded into some kind of the very small, the tiny NLP. So this was kind of the hybrid version of like we are basically mixing some of the 3D, the volume, the voxel representation, and also the neural network as well. So by combining these two kind of the representation, we could get some basically kind of like compressing the information while basically still getting some kind of the very high quality the outputs and also very fast the computation both in the optimization and also in the rendering. And there are also some kind of several ideas in terms of like how we can further compress all the information. Like one simple the idea was basically using the multi-resolution degrees. So now we are not having a single resolution degrees, but basically having some 8 grids that are basically having all different resolutions in a way that each of the grid are basically encoding either some kind of the global information or some kind of the local information. So we are combining the feature vectors coming from the all different resolution degrees, and then these kind of the feature vectors are basically decoded into the NLP. So this was kind of one of the idea that we can basically reduce the number of the feature vectors that are used for each of the voxels, while still basically maintaining the quality of all the output images. Yeah, so this was kind of example that we're having the one cell coming from this kind of the blue grid, and the other cell which is coming from the red grid, right? And also the other example was basically the spatial dehashing. So which is basically nothing but we are basically limiting the entire the number of all the feature vectors in the that can be used in all the corner points of the grids. Then basically we are allowing that the feature vectors can be assigned. One feature vector can be assigned into the multiple corner points. So this is basically kind of the case that we are having some kind of the hash table in terms of basically doing some kind of the assignment of all the feature vectors in our array into the corner points of the grids. Then probably there will be some of the cases that some of the different corner points are basically sharing the same feature vector. So that can be a problem. But basically, we are resolving this kind of issue basically by using the multi-resolution degrees, which means that while the two corner points might share the same feature vectors in the resolution of the grid, they may not have the same feature vectors in the other resolution of the grid. So in terms of basically combining the features from the different resolution of the grids, we can still have some kind of basically differentiate these kind of corner points while basically assigning the same feature the vectors into some kind of the other the corner points. So this was also the idea that we can use some kind of the spatial hashing in terms of like that we can limit the number of the feature vectors that we're gonna use, and also we can compress all the number of the parameters that we're gonna basically optimize. For those kind of the cases, still while reducing the number of the parameters to be optimized much smaller like this, so we can still basically achieve some kind of a very high quality the outputs. So this was kind of some sort of the engineering the idea in terms of like how we can manage the whole size of the parameters that we need to optimize while basically getting some kind of the good quality of the images. And then yeah, this was kind of the So if we basically use some more number of feature vectors, then we can also get some slightly better the quality of the outputs, while basically also sacrificing basically the memory consumption in terms of using much more the larger size of the memory. And also the good thing of like having this kind of representation is like more the spatial the representation having the 3D grid is that we can basically reduce the computation time like this. So these are all the results that are basically trained basically learning optimizing all the parameters in real time. So these are basically the real speed optimizing all the things. You can see that just like a couple of the seconds we can already see some kind of very nice results like this. MLP has shared weights for all the voxels. Yes, so that's the case. So we are basically making a small d MLP that is basically being used for all the feature vectors over all the corner points. So this was kind of the idea. So that's why I mentioned in the last time. So the basic idea is that instead of like making the one giant MLP that encodes all the global information, we are taking most of the parts of the MLP in a way that we are spreading those parameters as kind of feature vectors for each of the regions. So now all the feature vectors are basically associated with some kind of specific regions in the 3D space in a way that we are now all the parameters are basically some kind of the local parameters. So when you basically update each of the regions, we just need to update the feature vectors in that specific regions. So making this kind of spatial alignment from the feature vectors into this space in a way that basically we can reduce all the computation time. So this was kind of the idea that we discussed last time. Do you have any questions on this? So yeah, after discussing a couple of more things about some kind of some hybrid presentation for the NERD, we are also going to move on to some kind of new topic today. So one more the question that we have is that, so this was kind of some sort of the engineering the idea in terms of like how we're gonna compress all the kind of the information that we are encoding in the feature vectors using the multi-resolution degrees and also the spatial dehashing. And here the question is that would there be some kind of more like some sort of the algebraic way to compress all the feature vectors that are basically encoded in these 3D voxels? So that's kind of the one more the idea that we're gonna quickly see. So for that, we're gonna briefly see the idea about the matrix compression. So let's think about this kind of a case that we are having the matrix M here, and we are going to actually somehow compress the information that we're encoding in this D matrix. So how are we gonna do this kind of the matrix decompression? So that's basically a very common problem that we can see in many other the applications. And the typical way that we can do this kind of compression is that we are basically representing the given D matrix as kind of the multiplication of the row rank of the matrices. So the basic idea is that when you have this kind of the big matrix, we are representing the matrix as kind of the multiplication of the two very thin matrices in a way that the number of the elements in the matrices are basically becomes much smaller compared to the number of the elements in the input matrix, while the difference between these two becomes like very minimal, basically very marginal. So that's kind of the things that we are going to do. So here the question is that how we can find this kind of the two matrices, which multiplication becomes some kind of the good approximation of the given the matrix. So that's the basic idea that we're gonna briefly see. And for that, basically what we are going to do is that we are going to leverage the SVD that you should know if you took the linear algebra course. Is there anyone who did not take the linear algebra course before? Raise your hand. So everyone knows linear algebra, right? SVD. So yeah. So when you yeah. So when we basically do some kind of SVD, we can basically decompose the given the matrix DM into these kind of like three matrices, U and sigma and the V transpose. And we know that basically sigma is basically the diagonal of the matrix, that we are basically having the singular values for each of the element in the diagonal. And let's assume that now we sorted all the singular values in the sigma D matrix in a way that that's going to be arranged in the descending order. So the first one is the basically biggest value, and the second one is the second biggest, the largest value, and so on. So we are having this kind of the U, sigma, dV, and transpose these 3D matrices. And the given matrix, the M, is basically represented as the multiplication like these three things, right? Then here the question is that given the matrix with the rank N, how we can find a rank R matrix when the R is like much smaller than the N, that also minimizes the difference between the input matrix and the output the matrix. So basically, yeah, we are going to find this kind of the matrix using the SVD. So what we can quickly see is that if we basically rewrite all the things like this, so since the sigma is basically the diagonal of the matrix, now we can basically rewrite this kind of the matrix multiplication in this form. Let me show it. So you can see that these are basically the way that we can basically calculate the given the matrix the M. And we can also see that if we basically pre-compute these two components here, so this will be basically the same that we are pre-computing the U and the sigma, right? And then what you can see is that actually the given the matrix, the M, can be represented as basically the sum of the outer vectors of these two, the product of this kind of the two vectors. So what we can see is that once we basically do some kind of the SVD decomposition, then we can rewrite the same matrix DM as kind of the sum of the N components of the outer the products. So basically the outer product means basically having this kind of the product of the two matrix in a way that we can get the same size of the matrix of the N. Does it make sense? Yeah, so for all the cases, when you have this kind of the, for example, like let's say like we are having the simply like square matrix, M by N matrix, then we can basically see that like this kind of M by the N matrix can be represented with some kind of the N outer products. And we can say that each of the outer product is basically becomes some kind of a rank 1D matrix. So by basically accumulating all the rank of the matrix, now we can make the final rank N matrix. And then what we can also see is that without the proof, what we can briefly see is that if we basically first are the outer the products. So once we basically get this kind of SVD decomposition, after having the n outer the products, we can take some kind of the first R, this kind of the pairs of the vectors. So having the rank 1 the components, actually this becomes the best the approximation of the given the matrix with the rank R matrix. So this is quite simple, right? So if you want to basically do some kind of the matrix the compression, what you need to do is that especially when you want to limit the rank of the output the matrix to be R, which should be basically very smaller than the n. Then what we can do is that basically we can represent the given matrix as kind of the n component of the outer the products of the vectors. Then we can just take the first the R basically the outer the products. Then that becomes the best approximation, minimizing the difference between the input matrix and the output the matrix. So that's basically what we can do. So this is very simple the idea, then how we can do some kind of the long rank the approximation of the given the matrix, which means that once we basically get this kind of the SVD, we can just take the first the R, the number of the singular the values in the descending order, and also the corresponding the the singular the vectors as well. And then we can directly compute this kind of the two thin the matrix. One is basically the U times the sigma like this, and also the V like this. So this basically becomes some kind of the way that we can get some kind of the rank R the approximation for the given the matrix, which is become the same as basically we are having the R number of the outer the products, right? So this is kind of the very common practice that we can see for many kind of cases that when we basically want to do some kind of the matrix decompression. And actually we can do the same thing, not only for the 2D, the second order, some kind of the tensor, but also any kind of the order of the tensor. So we can see that actually the matrix is kind of the second order the tensor, that we're having this kind of 2D grid. So when you have the 2D grid, then we can just take the R number of the outer product of the two vectors. Then that becomes some kind of the way that we can do some kind of the rank R the approximation of the given the matrix. And also for the third order the tensor, when you have the 3D grid as well, the way that we can do some kind of the comparison is basically exactly the same. Now we are taking the outer products for these three vectors like this. So when you basically, once we take the outer product of these three vectors, if we have the R number of this kind of the outer the products, then that can be some kind of the one of the rank R the approximation of the given the tensor. So that's basically what we are going to do. So instead of like in the previous lecture, we have seen some kind of the ideas in terms of how we can encode all the information in the 3D grid. And now we are going to basically compress all these 3D grid information by taking some kind of the a few number of the outer the products in a way that we can do some kind of the best approximation of the information that we're encoding the 3D grid. So that's basically basic thing. That's kind of the things that we are going to do. So what we are going to do is that now we are going to compute the some kind of feature vectors in the voxels. And that is kind of some kind of the vectors in the for each of the voxel, but it's kind of the sum of the outer the products of the 3D vectors. So let's think about that. So actually, this is maybe not the feature vectors, but some kind of the scalar the numbers. Scalar the numbers. So let's think about like we are having the opacity values for each of the corner points in the 3D grid. So one way we can basically encode all this information is that we can directly encode all the opacity values for each of the corner points. And also the other way around in terms of like, especially when you want to do some kind of the compression, is that now we can basically have this kind of the three vectors encoding all this kind of the opacity information and taking the outer products of like all these three three vectors. And we are having some kind of the multiple, these kind of triplets in terms of that we are basically summing up all the outputs of the outer the products. So that's basically the one way that we can do some kind of the some algebraic decompression of the 3D tensors. So depending on the number of some kind of the authority products, we can control the level of the compression of all the information, right? But obviously, like especially in the case that when you have this 3D grid, if we want to do some kind of quite accurate approximation of the information, we might need to basically have some lots of these kind of the triplets, right? Yeah, we actually need to have some lots of kind of the triplets to basically get some kind of the good approximation of this kind of 3D tensor. So also the other way around we can do is that now we are decomposing the 3D tensor not into the triplet of the 1D vectors, but actually it's kind of the pairs of the like 1D the vector and also two-dimensional the grid as well. So this is another way that we can do some kind of the decomposition in a way that now each of the kind of the row length the component of the 3D grid is represented as the outer product of the 1D vector and the 2D grid as well. And we are having lots of this kind of the component in a way that we can basically also approximate the given the 3D grid. So this is kind of the case that we are having the 1D vector along this axis and the 2D grid in the other the two axes, and having some the number of these components. And we can also have the 1D vector in the other axis and also the 2D grid as well, having some multiple these kind of components. And we can also do the same thing for the other the axis as well. So by basically accumulating all these kind of the low length components, now we can also represent given the 3D the tensor with some kind of the approximation, while basically reducing the number of all the elements to be much smaller than the kind of the number of the elements in the given the 3D grid. So this is kind of also some kind of the interesting the idea in terms of like how we can reduce the number of the parameters in some kind of the more the algebraic way. Does this make sense? Any question on this? It is clear. Well, here one question might be is that, yeah, so this might be the case that when you have some kind of the 3D grid, right? So when you have the 2D or the 3D grid, especially for the 3D grid, then we can have this kind of the decomposition and then basically reproduce the same 3D grid with some kind of the approximation while basically reducing the number of the elements. So we can do these kind of things for the opacity values for each of the for the given the 3D grid. The problem is that we are not only encoding the opacity information, but basically we may want to encode some kind of the multi-dimensional the features, some kind of the vectors as well for each of the corner points. So the multi-dimensional the information can be either the speaker the harmonic the coordinates that we are using in the plane cell the idea, or some kind of the feature vectors, some latent vectors that will be basically fed as into the NLP. So those will be basically cases that we also need to encode some kind of the multi-dimensional the features, some kind of vectors for each of the corner points. Then what will be kind of the problem with this? Then the problem is that this might be actually the case that we are actually encoding not a kind of the third order tensor, but we're actually having the one more dimension, right? While we are having the three-dimensional some kind of the grid, for each of the corner points, we are having the one more the dimension, which is basically dimension for the feature vectors or the speaker the harmonic the coordinates, right? Then actually this will be the case that actually we need to basically somehow represent not the third order tensor, but actually the first order the tensor, right? Then what can you do? Actually, as we can see in the third order the case here. So let me, clean this up. So as we can see, the third order the case like this. Actually, there even could be some multiple ways to basically decompose the third order the tensor into the either just with the 1D vectors like this, and also kind of the combination of the 1D vector and the 2D grids, right? So also for the first order the tensor, we can do some kind of some multiple ways of the decomposition of the tensor. But just the simple way, the extension from the third order the tensor from the first order the tensor, it's basically just like adding some like one more the vector in the kind of the outer the products. So this can be the simplest way that we can simply extend the third order decomposition into the first order decomposition, but actually obviously there can be multiple the other ways to basically decompose the first order tensor into some kind of the lower order, some kind of the components. And also really this kind of the role is kind of the sum of the row rank, this kind of the components. So these are some kind of the algebraic way to compress all the information encoded in the either in the third order tensor or the first order the tensor. So the basic idea that we can apply this kind of idea in the NERF pipeline is basically that we are basically decomposing the third order the tensor, which is encoding the opacity information. And then we can also decompose the fourth order tensor encoding the radiance into some kind of the also the combination of the 1D vector and the 2D the matrices. And when we do this kind of the compression, actually what we can see is that compared to the planoxels, you can see that it becomes like much faster because of the number of the parameters is reduced a lot. So in the planoxel the case, the size of the parameters was basically more than 700 megabyte. And using basically this kind of compression, we could compress the size of the parameters into the almost like 70 megabyte, which is almost like kind of like 10 times like smaller than the planoxel the representation, which basically also results in basically a much faster the optimization and also the rendering as well, while basically also achieving even like the better quality in the rendering. So these are kind of the one way that we can also compress all the information encoded in these weight voxels. Okay, so a quick summary for all the things is that we also basically discuss some of the ideas basically in terms of like how we can reverse the voxel representation and also the speaker harmonics in terms of basically reducing the computation time. But this was also the case that we are basically consuming a large amount of the memory to basically speed up all the things. So the second thing was that basically how we can reduce this kind of the memory consumption using some kind of the multi-resolution degrees and also the spatial dehashing was basically the idea that we also discussed in the last lecture. And also there are some kind of the more the algebraic way in terms of how we can leverage this kind of the tensor decomposition in a way that we can also further reduce the memory usage while slightly also sacrificing the quality of the output images. So these are basically some of the ideas for the hybrid representation. Any questions on this? No? So yeah, actually there are tons of some kind of some follow-up work with the NERF. So you can actually check out some other papers as well. There are lots of the kind of the other representation as well. I just picked some kind of some of the representative, some kind of work, especially using some kind of some new representation for the NERF, basically the rendering. And there are also some kind of some examples that are leveraging some kind of the more explicit some geometric representation for the NERF pipeline. One of the kind of some notable example might be point NERF. So actually we have so when you have the questions, please post the messages on my host account, not the co-host account. If you post the message on my co-host account, I cannot see your message. Yeah. So when you have sorry, yeah, I guess still there are some people who are basically confusing my host and the co-host account. So if you send me the messages to my co-host account, it just like block some of my screens on the iPad, so I cannot just see your message, and also I cannot see my slide as well. If you have any questions, please post the messages to my host account. Yeah. So if I go back to this one, it seems like someone is like keep posting messages to my co-host account. So I guess. Sorry, 1 second. Yeah, that's my Post account. As I said multiple times, if you have any questions to me, please post the messages to my, send the messages to my post account. If you send the message to my post account, I cannot see the messages. So yeah, let me go over with all the slides here. So basically the thing is that, so we have seen some of the ideas basically in terms of like how we can encode all the information in a like more explicit way using the 3D grid. But instead of that, we can actually consider using some other representation that actually we also discussed over the course, like using the point cloud here. So here, basically, the basic idea is that for each of the multi-view images, now we are having some kind of the depth predictor, the neural network as well. So using this kind of depth predictor, we are making some kind of point cloud, some kind of rough reconstruction of the 3D. But obviously, this reconstruction may not be that accurate because there might be some kind of noise in the predicted point cloud as well. So what we are going to do is that instead of like encoding all the feature vectors into the 3D grid, as we have seen in the instant NGP, instant NGPD case, now we are encoding all the feature vectors into each of the points in the point cloud. And we can do the kind of same thing. Basically, when you basically shoot a ray for each of the sampled points for each of the along the array, now we can basically aggregate the features that are basically encoded in near the points in the point cloud. So this can be basically another way that we can leverage some kind of the explicit representation, which is not the 3D boxes here, but it's basically point cloud in this case. The question here is that doesn't the NERP also use a 4D tensor for RGBD? The NERP uses MLP, but I think I'm still missing what full volume field means. So basically, what do you mean by the NERP also uses the 4D tensor for the RGB signal? So the NERP is basically the MLP, the neural network, so which is basically not directly encoding all this kind of the information in some kind of the explicit space. So here the basic idea was basically we want to explicitly basically encode all this kind of the 3D or the 4D information in the spatial domain. So the idea of the Plano cells was basically encoding all this kind of opacity, the information as kind of per the corner points the value in the 3D grid. And also the radiance values are basically also encoded as kind of the extra kind of the one-dimensional the vector for each of the corner points in the 3D grid, which is basically making the 4D tensor. And then we want to basically represent all these kind of like the 4D tensor as kind of with some kind of the row rank the approximation. For that, we have basically decomposing the 4D tensor into some kind of some combination of the lower order the tensors, like the 1D vector and the 2D matrices, and approximating the 4D tensor as kind of the sum of the outer products of this kind of like 1D or the 2D the tensors. So that's the basic idea of the TensorRF, the framework. Does this answer your question? And here the idea was basically using the point cloud instead of the 3D volumes. And actually, we can also do the same thing, not only for the point cloud as well, but also for the mesh as well. So this is also kind of the example that we are now using some mesh representation, which is kind of the same. Now we are assuming that somehow we can get this kind of some rough reconstruction of the 3D, the objects or the 3D scenes from the multi-view images with a mesh. So basically making some kind of the triangulation of the point cloud in a way that we can get some kind of the rough reconstruction of the mesh. But obviously this may not be that accurate reconstruction because we are just leveraging some kind of the depth prediction or some kind of the other ideas. So given this kind of some kind of the rough reconstruction of some 3D, how we can also encode some kind of the features for each of the in this kind of the vertices or the faces in a way that we can basically render these things, and then using the NeRF pipeline is basically the idea in this paper. So what we can now do is that instead of like encoding all this information into the even the points or the faces, now we can even encode all this information into the texture image over the triangle, the mesh. Then if you took the comparative graphics course, what we can do is that as we basically like render the 3D objects with some kind of the texture information, we can do the same thing. We can use exactly the same rendering pipeline of the compare graphics in a way that we can basically rendering the mesh into the 2D images. But now the output becomes not the 2D color images, but the 2D images of the feature vectors. So that will be also the further decoded in a way that we can get some kind of the final colors as well. So this was also one of the examples that we are encoding all these feature vectors into the texture image of the triangle mesh in a way that we can rasterize, basically render all the things into the 2D the projection 2D view, and then we are having the feature image as the output of the rendering, and then we are further decoding all this kind of like the feature image into the final color image. So this was also kind of the one of the idea, and also this becomes like very compact and also very fast as well. So this is also leveraging all the advantages of using the explicit the representation in a way that we can also speed up all the optimization and also the rendering while also getting some kind of the good quality of the output images. So this is called the mobile NeRF, because like even this kind of framework can be even like implemented in some kind of the mobile of the platforms as well. And I guess some of you might know this work. I guess that even some of you are doing some project based on this work, which is the Gaussian splitting. This is another example that which is not using either the point cloud or a mesh, but using also a set of the 3D Gaussians as some kind of some explicit some representations. So this is kind of similar in terms of like using some explicit representation, but there the idea is not having any kind of the point cloud or the meshes, but having this kind of a set of the 3D Gaussians as some kind of the explicit representation, and the rest of the pipeline is kind of similar in high level with some point NeRF or the mobile NeRF, but they are basically switching the representation into the 3D Gaussians. So actually, this was the video that we have seen in the first lecture. And these are all the outputs of the NeRF using the Gaussian splitting the ideas. So you can see that the rendering speed is really fast, like having the 60 frames per second, while getting some quite good quality of the output the images. So these are the cases. Now we are representing somehow like approximating all these 3D scenes using a set of some 3D Gaussian some volumes, and then basically using some exactly the same volume rendering the idea, basically also encoding the feature vectors for each of the 3D the Gaussian, and basically rendering all the things using the same volume rendering the equation in a way that we can get this kind of the quality of the output images. Okay. Any questions on this? So we are a little bit behind the schedule. So let me quickly move on to the next topic. Yeah, so let me share my screen. Yeah, any questions? Okay, so yeah, is it okay with my screen? Can everyone see my screen? Yeah, let me move on. So far we have seen some of the ideas in terms like how we can leverage some kind of some other representation, especially to basically reduce all the computation time, while basically also getting some really good quality of all the outputs. So now we can see that the NeRF can be basically optimized, like very short amount of time, like just in like few minutes, and even also can be rendered in like the few seconds or even few milliseconds with some kind of very nice quality. So it seems like the issue with the computation time is kind of solved. But also there are some bunch of the other limitations as well. Actually, obviously, one of the kind of the sort of the limitation is that, like, we basically, in order to basically do some kind of the 3D reconstruction, we also need to basically have some lots of the multi-view images. And here also one of the question might be is that, can we also reconstruct 3D scenes only from these sparse view images? So that's basically what we are going to see here. Obviously, like if we only have some very sparse view images, it's really hard to basically get all the 3D information because even the input data does not basically provide all the 3D information, which means that if we want to basically reconstruct 3D only from these sparse view images, then we might need to have some kind of some prior knowledge that we can leverage in this kind of 3D reconstruction, which means that we might need to use some kind of information about like how likely the output, the object or scene will look like. So what the kind of the object or scenes that we are basically reconstructing, and what's the kind of typical the shape of some of the objects and the scenes that we are reconstructing. So that's basically some of the ideas that is about basically few shot or zero shot dinner, which is basically the case that we are basically doing some 3D reconstruction using dinner, using only the few number of the images. So how can you do that? Do you have any kind of thoughts in terms of like what would be some kind of some prior knowledge or some of the information that we can leverage for this 3D reconstruction when you only have some sparse view images? Question? Yeah, actually, you can actually see lots of the very recent work of like using some kind of some prior information for this kind of like the few shot or the zero shot, the nerve reconstruction. One of the simple idea for this might be basically using some depth information, as I actually mentioned in the previous slides. So if we have some kind of the depth prediction in your network, then what we can do is that for each of the images, we can first get the depth information, which is basically getting the 2.5 the information. And based on that, we can get some kind of the rough reconstruction of the 3D point cloud, and we can leverage this information to get some kind of the final the outputs. So that is also the case that we can leverage some kind of some depth priors. And also the interesting idea is basically using some clip embedding. So does everyone know the clip embedding? So clip embedding is basically the case that we are having some kind of the joint embedding of the texts and the images. So actually there are lots of kind of the data set that has the tones of some kind of the corresponding the pairs of the texts and the images. Now we can basically consider, so the clip is basically some kind of a joint embedding the space where basically we are embedding both the text and the images into the same position in the embedding space, in a way that we can see what are basically the text and the images that are basically somehow related to each other. So that's kind of some typical kind of the joint embedding things, and we can basically use this kind of some clip embedding in the many applications. And one of the ideas that the people tried in this kind of the diet dinner, the idea is basically checking some kind of the semantic consistency across the images. So what we can see is that, let's say, this is like, for example, like the example that we are basically having the images of this like the yellow, the bulldozer. So we are having the multiple images of the yellow, the bulldozer, but not that many images. Let's say we are having like less than 10 or the 5 images of the bulldozer. Then what we are going to do is that, so basically bulldozer should be bulldozer from any view, right? So if you see the bulldozer from the left, or from the right, from the back, these should be all the same, the yellow bulldozer, right? So which means that if the 3D shape has been reconstructed well, in a way that it really looks like the yellow the bulldozer, then if you render the 3D outputs from the any view, then all these kind of images should be mapped the same point in the clip embedding space. because their semantic meaning should be exactly the same, right? It is clear. So basically, the clip embedding is basically having some kind of semantic information, like what would be some kind of the some text description for each of the images. And if the images are from the same object, from whatever view, if the image is basically the yellow bulldozer image from the any view, then those images should be mapped to the same point in the clip embedding space. So what we can do is that while we are basically reconstructing the 3D shape with some kind of the few number of the images, we can basically check this kind of the semantic consistency in a way that we are rendering the 3D outputs from the arbitrary views and mapping them into the clip embedding space and checking whether they are basically mapped to the same point in the clip embedding space or not. Because if they are basically reconstructed as kind of the yellow bulldozer, then any images should be basically showing some kind of yellow bulldozer images. So they should be mapped to the points in the clip embedding space, because all these images can be described with the text description. So that's the very basic idea in terms of like how we can leverage this kind of clip embedding for some kind of some prior the knowledge to get some kind of the 3D objects from these perspective images. It is clear. Any questions on this? So yeah, this was kind of interesting. Yeah, now we can use this kind of clip embedding, and then we can reconstruct 3D objects even from these perspective view images. And then as kind of the next step, what we can do, actually, some kind of interesting the idea is that, so then do we really even need some kind of images? Let's do the NeRF even without any images. So here the idea is that now what we are going to provide is even not a image, but let me just provide a text description. So let's train a NeRF in a way that when you basically render this 3D object into any arbitrary views, those are only mapped to the same point with the text that we are providing in the clip embedding space. So this is kind of the extension from the few shot to the zero shot. So now we are basically doing some kind of the NeRF reconstruction, even without any images, but just by giving some kind of the prompt, the text prompt. So the input is only the text, and we are training a NeRF in a way that when you render the NeRF into any views, all the images are mapped to the same point with the text in the same clip embedding space. Obviously, there are lots of some details in terms of how we can really get some kind of the good quality of the outputs, but that's basically the high level the idea. So how we can train a NeRF even without any images, but using only the text prompt. So that was the first work that we could see last year, which is named as the Dream Fields. And these are some of the outputs. So you can see that the outputs looks like funky, like it doesn't look like some kind of realistic kind of things, but some kind of interesting the outputs. So we can see some kind of some arms shape, armatures in the shape of something. So it's like armature with the shape of the avocado, or armature with the shape of the pumpkin, or something else. So you can see some kind of the interesting, some imaginary, some kind of the outputs by just using this kind of the framework, which is training the NeRF even without images. So this is kind of the interesting the idea. So now what we can see from this kind of the output is that this is not anything about like 3D reconstruction. So now we are not having any kind of the information, like some images or something for the objects or scenes that we are going to reconstruct, but we only have some kind of the text description. So now we are moving on about like the generation, not the reconstruction. So even without the images, can he also produce any kind of some 3D outputs? Only have by some kind of the some text description. But these are also all the cases that we are using some kind of these 2D priors, some priors in terms of like what would be some kind of some realistic images that are also corresponding to some kind of given the text prompt. So by leveraging this kind of some information about like what are some kind of the realistic images that we're gonna see for given the text prompt, can we do some kind of the 3D generation? So this is basically also kind of the topic that we are going to discuss from this week. And also the question is that instead of the clip, can we also use some kind of the other, some BJD models that also have some kind of 2D priors? And for that, basically, what we are going to discuss is the diffusion D models. Diffusion model, basically, I guess some of you obviously have heard about the stable diffusion or the image journey. So these are some kind of the very recent, some kind of the image, the generative models that can also produce very realistic images. So those are all the images that are actually generated by the AI, the techniques using the stable diffusion here. And these are basically only based on the recent the diffusion models. This is kind of the idea for the generative models. So by using this kind of the 2D generative models, having this kind of like generating this kind of like high quality images, can you also reconstruct, not reconstructing, but actually generating some 3D? Can you do some kind of 3D generation using this kind of some 2D priors that are learned from this kind of the 2D image generative models? So this is kind of the question that we are going to discuss from this week. Any questions on this? So we are not having enough time to discuss all the details for the diffusion models, but I guess we will need to spend this week and also the next week as well to basically discuss all the ideas in the diffusion models. And diffusion model is also about the things about the assignment 3. So also the deadline for the assignment 3 is November 12th or something. So basically, if you want, when you need to do the assignment 3, you also need to basically go over with some kind of the background in the diffusion models. And also the slides that I prepared are basically some slides for as kind of the basic introduction for the people with any kind of prior knowledge for the diffusion models. So we are not gonna get into the very deep into all the ideas. Obviously, if we want to go deep into all the ideas for the diffusion models, then we need to spend the entire semester for that. However, we're gonna still basically dig into some details of the math along the way. So please be prepared to see some formulations there. And also I recommend you to basically check out all the details in the math even after the lecture. So that's basically what we are going to do. So let's basically see the very high level, the basic idea for all the generative models. So basically what we are going to do in the generative model is that we are going to learn some kind of the data distribution. So let's think about some kind of the domain where all the data basically live. And here, basically, we are going to learn the data distribution. So basically, data distribution basically means like, some kind of the probability density function that indicates like how likely the data at each of the point becomes some kind of the realistic data. So this may not be that kind of the intuitive. So let's think about some kind of the, please mute. Yeah. So yeah, one of the example might be is that. So let's think about the case that we are having tons of the RGB, the color images with the resolution of the 128 by 128. Right. So let's think about like having a set of the images. And then what we can see is that we can basically somehow consider this set of the images as kind of the points in the very high dimensional space. So actually, if we consider the space with the 128 by 128 times 3, because basically each of the image is basically represented with this amount of the numbers, right? 128 by 128, and then we're having the RGB 3 channels. So we basically need 128 by 128 by 3, the number of the elements, the numbers, to represent a single image, right? Then what you can see is that we can actually consider that all the basically images become a single point in this very high dimensional space, right? So the image is basically a single point in this high dimensional space, and then we're having some kind of a set of the points in the very high dimensional space. And we now want to learn a distribution over this kind of the high dimensional some kind of the space where we are basically embedding all the kind of data in a way that the distribution basically indicates like how likely the point in the given space becomes one of the realistic the data that we want to see. So that's basically what we are going to do. So obviously, if we basically randomly sample any arbitrary point in this kind of the high dimensional space, that will not be any kind of some real the photo image, right? So any, if we basically randomly sample any point in this space, that will be basically having some of the images with having some random, some arbitrary colors. So that's not the image that we want to see. There might be very specific some of the types of images that basically looks like some kind of the real image, where the image is in some specific domain, and those images might be a subset of the points in this kind of the high dimensional space. And here the goal is to basically learn this kind of the distribution of the realistic images in the high dimensional space. And here now we are only seeing the one-dimensional kind of the example. So let's say like all the data is basically living in the 1D space. And the thing is that we don't know the exact data distribution because we're going to have some kind of the limited amount of these samples. So the information that we have is we are not having the real the data distribution in the space, but we are only having some kind of the samples in the given space. So based on this information, like what we are going to do is that yes, we only have the samples of the data. So given this kind of the samples of kind of the data, what we are going to do is that we are going to gradually transform the data distribution in a way that at the end of all the transformation, the output becomes this kind of some simple distribution, which is typically the unique Gaussian. So we're gonna call this as kind of the target distribution. Sorry, I'm calling this one. This is target distribution. And what we are going to do is that we are going to gradually basically convert each of the data distribution in a way that it finally becomes this kind of the target distribution, which is the unique Gaussian. And actually, the way that we are basically making this kind of transformation is actually quite simple. What we are going to do is that for each of the points in this space, we are going to just like perturb the position of each of the point or with some kind of a small Gaussian noise. So when you have this kind of like each of the point here, we are having this small Gaussian in the local region and randomly sampling the kind of the next position in the space. And we are moving each of the point into some kind of the sampled point, sampled based on the small the Gaussian, the local Gaussian here. So we are basically getting this kind of some transformation. And the thing is that if we repeat all this process, then at the end of the day, we're gonna basically get this kind of the unique Gaussian. And we're gonna see, why it works. So that's the kind of things. So that's kind of thing. So what we are going to do is that we are going to basically map the given the data distribution into the unique Gaussian distribution. So if we can basically have this kind of the mapping from the given the data distribution to the unique Gaussian, and also if we can get the reverse way, or like mapping the unique Gaussian into the data distribution, then now we can basically sample the distribution, so sample the data based on the this kind of mapping. So the thing is that while we don't know the given the data distribution, if we basically have the mapping from the unique Gaussian to the data distribution, then what we can do is that we can just sample based on the given the unique Gaussian distribution and basically do some kind of the inverse mapping to become the one of the samples in the data distribution. So that's the basic idea. So instead of like directly getting the data distribution, the information, which will be very complicated, what we're going to do is that we are basically getting the mapping from the this target distribution to the data distribution in a way that in the generation the time we can sample from the unique Gaussian and then map this into the one of the points that is to sample from the data distribution. And for that, we are also first going to basically convert the data distribution into the unique Gaussian in a way that we can jointly learn the other way around, the mapping from the unique Gaussian to the data distribution. So that's basically what we are going to do. Is this clear? Any questions on this? So this is basically what we are doing for all the generative models. And this is like one of the examples in the 2D case. Starting from some kind of the data distribution into the mapping that into the 2D Gaussian, and doing some kind of the reverse mapping from the unique Gaussian to the data distribution again as well. So let's say this kind of like the Swiss roll kind of thing is kind of the data distribution, and we are mapping this into the to the unique Gaussian. And if we can also do some kind of the inverse mapping from the unique Gaussian to the data distribution, then we can sample from the 2D Gaussian and then map this into one of the points of the data distribution. So that's basically what we are going to do. Any questions? Please post your questions to my host account. Yeah, so what you can see is that basically the goal is to basically map the target distribution or the prior distribution into the data distribution in a way that we can do some kind of sampling from the target distribution and mapping that to all the points in the data distribution. So especially in the diffusion models, we are going to make both the target distribution and the data distribution to be the distributions in the same dimensional space. And also as the target distribution, we are going to use the unique Gaussian distribution as our target. So that's basically what we are going to do. And as I said, this is like the very common thing for all the other digital models. Basically mapping from the prior to the data distribution. In the test time, what we can do is that we are sampling from the prior and basically mapping to the data distribution. So let's briefly see how we can do these kind of things for the other generative models as well. So obviously you would know the architecture of the GAN here. So if you recall, is there anyone who has zero idea about the GAN here? I did not learn about GAN before. Raise your hand or post messages. GAN, VA, things. So yeah, let's quickly go over with some of the ideas, the GAN and the VA. So basically, you don't know GAN or the VA, is okay to understand the different models. But basic idea of the GAN is that it's also the same. It's basically mapping the prior distribution into the data distribution. The thing of the GAN is that we only learn this mapping prior to the data distribution, but we are not learning the other way around. Because this is the only thing that we need to learn, right? So this is the GAN architecture. But we need to check. So when we basically learn the mapping from the prior distribution to the data distribution, we need to check whether the output, the point after the mapping is really a sample from the data distribution, right? So once we basically sample from the prior distribution and map to the some data distribution, we need to check whether this mapping is correct, right? Whether the point is really mapped to one of the sample of the data distribution. And for that, we are basically having another neural network, which is called the discriminator, which is basically checking whether the output of the mapping is really one of the point in the data distribution or not. So basically checking whether the output data is real or the fake. So this is basically the idea that we are having the discriminator and having the adversarial training to basically check whether the output is real or the fake. So this is kind of one of the examples that we are learning the mapping from the prior to the data distribution, but not the other way around, but basically having the discriminator to check whether the mapping is correct or not. So like there are lots of the issues with the GAN. So when people started to see the other way around, which is having the both way of the mapping. So now the VAE is basically having the mapping from the data to the prior distribution, and also prior to the data as well. So by having this kind of the two mappings, learning these two mappings jointly, now we don't need to have the discriminator. So without the discriminator, we can basically jointly map these two mappings and get some kind of the some good mapping from the prior to the data distribution with some kind of the KLD divergence loss. But also there are lots of the issues with the VAE. So we're gonna get into the problems of the VAE at the end of all the things. And also the flow-based model is kind of some of the extension of the VAE in terms of that now we are having the the decoder, the mapping from the prior to the data distribution as the inverse of the encoder data to the prior. And also we are having some kind of the iterative process to get each of the mapping. So that's the idea of the flow-based model. And now we are having the diffusion models. And some of the important properties or the characteristics of the diffusion model is that now we are having both the encoder and the decoder. So basically encoding basically means that we are having the mapping from the data distribution to the some prior or the target distribution. And the decoding is the other way around, from the prior to the data. And both of these kind of the process are basically some iterative procedure. So we are also getting to the idea of like, you know, why we are going to have the iterative process. So that's kind of thing. And also the characteristic of the diffusion model is that while we are having both the encoder and the decoder, the encoding process is not learned. The encoding process is fixed. It's kind of given the procedure. So while we are fixing the encoding procedure, we are only learning the decoding procedure. So that's kind of interesting, some characteristics of the diffusion models. And also for the diffusion models, both the prior distribution and also the data distribution should be in the same dimensional space. So those are some kind of the characteristics of the diffusion models. So if we compare all these kind of the different degenerate models, you can see that again is not the case that we're directly somehow getting the data distribution. But from the VAE flow model and diffusion models, we are basically more explicitly modeling the data distribution. So that's kind of thing. And also GAN does not have the encoding the network. And also diffusion, while the diffusion has the encoding the process, we do not have the encoding the network. So we are also, that's kind of the things. And GAN is the case that we're having the adversarial the training, basically having the discriminator, which is checking whether the output is like true or the false. And also the flow-based model and the diffusion, these two are basically the cases that we're having some kind of the iterative procedure. We're gonna see at the end like why this kind of iterative procedure can improve the performance. And also diffusion model is the only case that they are basically having some kind of the target and the data distribution in the same dimensional space. And some kind of the limitations of each of the previous work is that basically the GAN is quite unstable. So you need to be very careful when you train the GAN. Otherwise, in most of the cases, you can get some very bad quality. And we can typically see some kind of the cases of the mode collapse, which is the case that we are not getting the entire diversity of the data that we want to generate. While VAE is like more stable in terms of training and also does not have the mode collapse issues, the quality of the output is typically much worse. And the flow-based model is basically improving the quality a little bit, but still the quality may not be the best compared to diffusion models, and also it's quite slow. And we're going to also see some kind of limitations of the diffusion models at the end. So that's basically. So let's briefly see the basic idea of the one specific diffusion model, which is called the denoising the diffusion probabilistic models, which is the most famous diffusion model. So we're going to basically see this idea. So let's briefly see the basic idea here, and let's continue on Wednesday. So we're going to have both the forward and the reverse process. So as I shown in the previous slides, forward process is the process that we are basically perturbing each of the data in the data distribution in a way that we can transform the given data distribution into the target distribution. And this is like not the process which is learned, but this is kind of the fixed process. So we are basically making some kind of the Markov chain, basically adding some kind of Gaussian noise for each of these steps in a way that the output of the transformation becomes some kind of the unique Gaussian distribution. So for each step, basically we are adding some kind of the noise for each of the data point. We are going to add this kind of the Gaussian noise, which is basically designed like this. So this is really designed, which means that we are basically controlling these two parameters in a way that basically we are basically shifting all the things to some kind of some random points. And when we basically accumulate all these kind of the process, we can get some kind of the one-step transition from the original data point into some kind of data point after the t time step. So this is kind of the full the process. And our goal is that while we are making this kind of some kind of remarkable chain process, basically stacking like the process, like adding the Gaussian noise in the full process, our goal is that we want to also, sorry, let me skip this. Our goal is also to make the reverse process as kind of the another the Markov chain process, while also basically having this kind of the Gaussian transition. So the fourth case was basically starting from the let me go back to here. The default process is starting from our data distribution, QX0 here, and then we are basically mapping this into the target distribution PXT here in a way that we are basically adding some kind of this small Gaussian noise multiple times over time from over the T steps, right? So we are starting from the QX0, and then at the end of all the T times of the transition, we are basically mapping all the things into the PXT, which is the unique Gaussian, right? And the reverse process is basically doing exactly the same thing, but now mapping the PXT into the QX0. But by also doing some accumulating some kind of the Gaussian transition like this. So here, all the kind of the thing is that while we are basically having some kind of the fixed transition of the full process like this, given this kind of the fixed the full transition, the goal is to basically learn this kind of the reverse transition for each of the time. So if we can also basically somehow learn this reverse the transition, which basically becomes the inverse function of the for the process, then as I said, we can do this kind of the sampling. Basically, we can do sampling with the target distribution and then map all the points into the points of the data distribution. And that becomes our generation process. Is this clear? And as kind of some loss function of the neural network, at the end of the day, what we are going to do is that once we do this kind of the mapping, like sampling from the target distribution, and to do this kind of the transition multiple times in the reverse way, and at the end of the day, basically when you basically check this probability, the values of the output, the density function, with the given samples that we have. So for the data distribution, we're going to have some bunch of the samples that we have. For example, some of the images that we are having some image space. Then we're going to check whether the probability values for each of the samples that we have has some kind of the high values. So we are going to optimize all the things in a way that we are basically maximizing the log probability of the samples of basically the probability values of the density function that we are basically learning in this way as kind of the composition of the target distribution and the multiple times of the reverse transition. So that's the basic idea. So we are basically having some symmetric functions for the process. We are starting from the data distribution and doing some kind of the T steps of the Gaussian transition in a way that we can map this into the target distribution. And in the reverse process, we are going to do the same thing. Now we are going to basically map the target distribution into the data distribution by just also applying some multiple Gaussian transition in a way that the probability for the data that we are having becomes like the maximized by basically optimizing this reverse transition. So that's kind of the things that we are going to see. And then there should be multiple questions, right? The first question might be is that, we are basically just applying some multiple Gaussian transition here. Then why does this become the unique Gaussian at the end? So when you basically apply this kind of the Gaussian transition the multiple times, why does the output becomes the unique Gaussian distribution? So that might be the first question. And the second question is that also here, basically when you have this kind of the fixed the process, how we can learn some kind of the prompters for this kind of the reverse process. So this might be basically the two main questions that we need to think about. So we're gonna discuss all this idea from next Wednesday, and we're gonna resume next Wednesday. Any question? Yeah, the flow-based model also should be in the same dimension. Sorry. Any other big questions? So yeah, that's kind of the typo. Any questions for the models, for the different models? So yeah, we're gonna continue like discussing the different models on the Wednesday, and I actually recommend you to check out some of the math in the slides before you join the lecture next time. So let's continue next Wednesday. Yeah. Bye.